In this example, we're going to find the power series solutions of the given differential equation about the ordinary point x equals 0. Then the solution will be in the form of y of x equals the summation cn x to the power n from 0 to infinity, or in the form of c0 plus c1 times x plus c1, c2 x squared, and so forth. Then the y prime is the summation of the n, cn x to the n minus 1, n starting from 1 to infinity, and the y double prime, or the second derivative, is the summation of n times n minus 1 times cn x to the n minus 2, n starting from 2 to infinity. Now we are going to substitute y and y double prime into the equation. For the y double prime, we have the summation of the n minus 1 times cn x to the n minus 2, n starting from 2 to infinity, plus the summation cn x to the n starting from 0 to infinity for the second term equals 0. Next, we are going to get the common index by replacing n with some k factor. We're gonna let k be n, or just replace n with the k for the second summation. The first summation, we're gonna let k be n minus 2, or k plus 2 equals n for the first summation. Then we're gonna get the summation k equals 0. As n equals 2, k gonna be 0. N is replaced with the k plus 2. N minus 1 is replaced with the k plus 1. C subscript n now becomes C subscript k plus 2 times x to the power k, plus the summation k equals 0 to infinity ck x to the power k equals 0. Now we get the common factor x to the power k. We're gonna factor x to the power k out. And before we do that, let's check the index starting at the same k value, so that we can combine these two summation into one. So summation k equals 0 to infinity with the common factor x to the power k, the coefficient of the first one as k plus 2 times k plus 1 multiplied by ck plus 2 added by ck as a coefficient of the second summation with the common factor x to the power k equals 0. Then we are going to equate the coefficient of the left and the right of the same term. The right hand side is 0. That means you have the 0 plus 0 times x plus 0 times x squared plus 0 times x to the third, and so forth. Or we say all coefficients are 0. Equate with the left hand side. So for k greater than or equal to 0, we have the relationship as k plus 2 times k plus 1 times ck plus 2 plus ck equals 0. Now we are going to rewrite the ck plus 2 in terms of ck. ck plus 2 equals negative ck divided by the product of k plus 2 and k plus 1. And this formula is called the recurrence relation. And we use it for k greater than or equal to 0. For k equals 0, we obtain C2 as negative C0 over 2 times 1, or negative C0 over 2. For k equals 1, we obtain C3, which is negative C1 over 1 plus 2, which is the value 3 multiplied by 2, or negative C1 over 6. and k equals 2, we obtain C4 as negative C2 divided by 4 times 2, times 3, sorry. As we get C2 equals negative C0 over 2, we can replace C2 with the term that we know, or negative 1 over 4 times 3 multiplied by negative C0 over 2, or we can rewrite this as C0 over 4 times 3 times 2, which is C0 over 24. Let's find a couple more. For k equals 3, we get C5 as negative C3 divided by 5 times 4. And again, the C3 is in the form of negative C1 over 6, and negative 6 is 3 times 2. Now we get C1 divided by 120, and keep doing the same manner to find the next coefficient. As you recognize the pattern of the denominator, the 2 times 1, this is 2 factorial. The 6, which is 3 times 2, or 3 factorial. For the denominator of the C4 is 4 times 3 times 2, or 4 factorial. Similar way for the denominator of C5, which is 5 times 4 times 3 times 2, or we can say 120 is 5 factorial. As we recognize the pattern, it's easier to write the solution form after we obtain all the terms or the coefficient. Now, we put them together as the power series solution of this differential equation. As we assume C0 not equal to 0 and also C1 not equal to 0. Otherwise, we get trivial solution. We get the y at x as the C0 plus C1 times x plus C2 times x squared plus C3 times x to the third, C4 times x to the fourth, and one more like C5 times x to the fifth, plus and so forth. Using the terms, the coefficients that we found as C0 and C1 are not 0, the C2 is negative negative C0 over 2 times x squared. And C3 is negative C1 over 6, which is the 3 factorial, x to the third, and 2 as 2 factorial for the coefficient, denominator of the coefficient of x squared. And C4 is C0 over 24, which is 4 factorial. C5 is C1 divided by 5 factorial, x to the fifth, and so forth. Next, we're going to regroup by collecting the terms with the common C0 as the common factor. We get 1 minus 1 over 2 factorial x to the second plus 1 over 4 factorial x to the fourth. If you make a prediction for the next term, we would get negative 1 over 6 factorial x to the sixth, and so forth, plus the second group as the common coefficient C1. We get C1 multiplied by x minus 1 over 3 factorial times x to the third plus 1 over 5 factorial times x to the fifth. And we can make a prediction for the next term as negative 1 over 7 factorial times x to the 7, and so forth. As you recognize the pattern of the series expansion, the first group here is the Taylor series expansion of the cosine function, and the second one is the Taylor series expansion for sine function. And we can see this as C0 or the first coefficient. I'm going to write it as the C1 star, and the C1 from the process is the C2 star. As we see the solution as C1 star multiplied by Y1 plus C2 star multiplied by Y2, or in the form of C1 star multiplied by cosine x plus C2 star multiplied by sine x as the solution. This is similar. This is the solution that we are familiar with. Back to chapter 4. For the differential equation y double prime plus y equals 0, this is the differential equation with the coefficient as a constant. If we look at the auxiliary equation, which is m squared plus 1 equals 0, so then we obtain m, the value m as the plus minus the conjugate number I, the complex conjugate I. That leads to the solution y equals C1 cosine x plus C2 cosine C2 sine x.